Okay, hello. Thank you for coming out here today. Let me know if I'm not loud enough, please. I can't tell if my speaker here is working. I'm Laurice Wuffel. Those of you who have been here in the past, in the previous meetings, have met me before. If not, then I'm from Indiana University, working at the Quest Center with Andrew Lumsdaine. Now, I started this work as a PhD student for Andrew, and I just defended my thesis about 2 weeks ago. So since then, we're just kind of, oh, thank you. Thank you. So now it's basically work that we're looking forward to continue working on in the future. So I guess I must have done something good. I don't know. So today I really want to cover these three main topics. The first thing is kind of just talk about what concept Clang is actually about and where it's headed. One point I want to make here is that I would eventually like to open this up for contributions. There's only so much that one person can do, right? So, and there is still a lot of different directions that we can take this project into, and I would like to talk to people who are interested. I know I've received a couple of those emails, so just keep talking to me and then we'll see what we can do. The main point of this talk is to the second point is to highlight the kind of theoretical progress that we're able to make just by thinking about full concepts. It's important to note here that these progresses actually go beyond C++ and concept itself and addresses issues with programming languages in general. So it's kind of cool. I talked about the first two ones last year, the name binding framework and the weak hiding scoping rule. And this one, I haven't talked about it yet, and we're kind of going to go over that today. We're actually going to go over all these bullet points with the aid of some practical examples, and let me know if you have any questions. Hopefully we'll learn something. And I'm going to end this talk with some comparative study that we have on the way based on these current findings and also a combination of that with previous work. So this is probably the best way that I can summarize what I've been up to. And this is also probably a testament of what our lab Quest does. We spend a lot of time trying to bridge the gap between practical interest as well as theoretical interest. So when it came to concept, it was basically like, on the one hand, we have this nice theoretical notion of concepts which can be traced back to algebraic specification languages like Tecton. Some people have done work on formalizing that with institutions. Jeremy Sieg has extended the System F with concepts. Several other work in between. And then on the other hand, we have this vast array of practical applications that use C++. And our goal was, can we actually somehow bring the best of both worlds together and get something like concepts in C++? So concept Clang is supposed to guide the design of concepts for C++. That's our goal, ultimately. And we're trying to do this from an implementation perspective by extending Clang with concepts. And there are more reasons to that that we're going to go over. Now, concepts themselves are not really a new notion, right? If you've worked with type classes in Haskell or signatures in ML, you've kind of seen them in some capacity. It's not exactly the same as concepts in C++, but you can already kind of build an intuition based on those. In C++, they drive the design of template libraries. So why do we want something like this? Oh, I'm having some cropping there out of the... So here I have a vector of elements of type void star. And I want to sort those elements. And I pass in a less than operator that is expected to act on elements of type int. Should this be a valid program? The compiler doesn't think so, and rightfully so, right? But the problem is, when you look at this, it's kind of hard to decipher where the problem actually came from. Who is to blame here? The author of sort or the user of sort? And how to actually even begin fixing this error. And not only that, these error messages are pointing to the internals of the library implementation. So you get like library details leak into user space, which in general you kind of don't want to see happen. Also, depending on how deeply nested that call is, you can actually get error messages that are as large as 500 megabytes or even 2 gigabytes. I believe Jeremiah Wilcock, one of my people I'm working with on this project, I've heard he's kind of famous for generating these kind of error messages in the past. So all we want the compiler to tell us here is that the binary operator is not compatible for sorting elements of that type. Now here's another problem. We now have a vector of integers. And we're trying to sort them, and we do pass an operator that acts on integers. But it's a not equal to operator. Does it make sense to sort things with not equal to? The compiler doesn't. The compiler thinks so. But even STL tells us that should not be the case. So you get situations like this where you have semantic errors that are not captured by the compiler. And we kind of don't want that to be the case, right? So using concept-clang, we can actually capture the, we capture the error that we were able to capture before, but this time the diagnosis is very short. This is about how long you would ever expect it to be, the message to be. And you can see here that the very first thing that you see is an indicator in user code of where the problem came from. So here it says, this is where the problem came from, and then we have some additional notes thanks to the beautifulness of Clang that gives us a little bit more information. And we can also capture semantic errors. Same thing. So the reason why we want concepts in C++ is because we need separate type checking. There has been several other idioms that have been developed and used over the years based on reusing features of C++ and also kind of like staying at the level of the library or preprocessor. But those also have kind of, as amazing as they have been, they've kind of all reached their limits in some sense, in terms of verbosity, expressiveness, and you name it. And over the time, it's become very apparent that we just really need language support for concepts. And this is where concept-clang comes in. So concepts are not new to C++, like I said. They were first introduced around 1993, and then they eventually drove the design of the STL around 1998. And like I said, most of the libraries today are designed with concepts in mind. When it comes to supporting concepts as a language feature, this is where we start having a little bit of a, trouble getting somewhere. Starting 2003, there were these notion of implicit concepts, and here the idea was that we wanted to prioritize simplicity and things like backward compatibility with unconstrained C++ programs. And then 2 years later, explicit concepts came up, and this one was emphasizing more expressive and generic power. Now, these were kind of two diverging design philosophies, yet they each have their drawbacks and also advantages. The implicit concepts was championed by Bjarne and Gabriel and a lot of people from Texas A&M, and the explicit one was championed by people from my group, actually. Marcin Zaleski, well, he wasn't there at the time. Jeremiah, Jeremy Sick, Jaco, myself, Ron Garcia, a lot of different people. So eventually, it became apparent that we really need to reach a consensus. And we actually started working towards that consensus. 2009, we almost had it until we didn't have it. Essentially, the idea was that it was just, we didn't have enough information to know that we can proceed with confidence with this design. So we needed to take a little bit of a step back and think about it a little bit more. 2011, we started revisiting the design from a different perspective. So some people from my school, I think it was me, Jeremiah, and Marcin, and Lumsden, we went to Palo Alto and saw Andrew Sutton, Bjarne, Sean Parent, and Alex Stepanov, and several people from the field. And we kind of the point was, we were trying to see if there is any way that, well, let me rephrase that. So before, all the approach up until then were kind of doing it from the perspective of an implementer for concepts. And what we're trying to do was to see, let's see if we can look at this from a different perspective. Instead of focusing so much on how to implement them, let's try and see, actually, look at it from the perspective of the library designer. What are concepts? How should they be used? How can you actually exploit them to design good libraries? And we came up with a set of guidelines, like, for example, it doesn't make sense to have concepts that don't have semantic content, and several other guidelines. And we focused on the STL, on a very specific subset of the STL as guide, just to see what will happen in the future. Now, the thing with the Palo Alto concepts was that we were so focused on how to use them that we didn't address the language mechanics. So me, the implementer, I can look at the Palo Alto design, I know how to use it, but I have no idea how to implement it because it doesn't tell me how to do it. I can look at the pre-framework proposal and I know exactly how to implement it, but it's also limited in some ways, which is the essence of the theoretical progress that I've been making. Now, recently, Concepts Light came, and the way I view Concepts Light is kind of like a step 0 towards providing the language semantics for the Palo Alto proposal. They're starting very, very minimally, only checking the surface of concepts and focusing on template uses. But even while focusing on template uses, they're still missing some aspects that are very crucial to checking the uses of templates. So far, we still don't have any consensus on how to design concepts for C++. Despite everything that has been going on, the discussions, when it comes to full concepts, are still more analytical than concrete. And we would like that not to be the case anymore. And this is why I bought ConceptClang. With ConceptClang, the idea is that we should be able to take any program and just say, hey, run this in pre-Frankfurt mode and see what happens, and run this in Palo Alto mode and see what happens. And there are also different variants of those different modes that my job is kind of to identify and make available in the compiler for people to play around with. So ConceptClang picks up where ConceptGCC left off. We had an initial prototype immediately after the pre-Frankfurt design was pulled out of consideration. That prototype was actually one of the main reasons, one of the main drivers behind the Palo Alto meeting. So it was one of the reasons why we decided to actually meet and start looking at this from a different perspective. With the first prototype, the way that it was presented, the idea was that well, you know, we can actually implement concepts generically, independently of a lot of the details that had been having people focused on more than a lot of things that you should probably be focusing on too. Like the idea is that there's a lot of other things that concepts really need us to focus on besides those design-specific details that had been the main point of all the discussions. So here I'm saying it can be implemented generically, but coming out of Palo Alto, given the differences in approaches and all that, and different factors like that, I had to actually make it generic. I had to go from, hey, this can be generic, to saying, hey, this is actually generic. And that's what I've been working on over the past few years. So like I said, it implements concepts in the design, independently of design-specific details. And something that is particularly different from previous approaches is that it treats components of concepts as first-class entities of the language. That way we can actually have a really good idea of how a given design affects the language. Our primary focus is the pre-Frankfurt and Palo Alto designs, and Concepts Light comes as an extension of the Palo Alto design. It basically comes for free because it's one particular variant of it. So for the rest of this talk, I'm going to kind of quickly brush over the definition of concepts and the implementation structure in ConceptClang so that we can get to what I consider the juicy part, right? The name binding framework and all that stuff, and then the comparative study. So concepts are a feature for generic programming. I know you guys have probably heard a lot about generic programming by now. In C++, it's supported using templates. And what concepts do is it allows us to constrain those templates based on the properties that must be satisfied in order to use this function. There is a lifting process that goes from concrete algorithms, like you can think of it as a summation of integers, a summation of elements in an array of integers, or a summation of elements in an array of floating point numbers, or a multiplication of elements in an array of integers. So you can lift all those concrete algorithms up to something more generic like this. The algorithm actually is what drives the concept. So you go from the internals of the algorithm, you notice syntactic properties like these, the existence of those operators, prefix operator and similar stuff. There are semantic requirements and also complexity guarantees. And all those things, you notice them and decide to express them in a concept and group them together, express them in a concept, and you get something like this for the input iterator, for example. This is using the pre-Frankfurt syntax. Yes? Sure. Yeah. Okay. Sure. Sorry about that. So yeah, so you use concepts to express all those requirements on algorithms. And particularly to concepts in C++. And the interesting thing here is that actually a lot of these properties of concepts that are particular to C++ have actually been slowly adopted in other languages like Haskell. So one particular property is that if I go from a concrete algorithm like this one to a generic algorithm like that one, there shouldn't be a penalty. There should be no penalty. Well, what's the word? I can't speak today. There should be no performance complexity penalty from using this one and that one. Does that make sense, guys? Okay. Also, whenever it is possible to provide a specialized form of a given algorithm, maybe for greater performance, you should always make that available. First, define it and also make it available to the user. And what we just saw at the beginning of this talk is to preserve and improve safety, which brings us separate type checking as well as better error detection and diagnosis. So now, thinking about all the components of concepts, you can kind of group them into these three main components. On the one hand, we have concept definitions. We have constraints template definitions. Here, these are typically constrained by the concept. So actually, I should show you something. So this is called the requires clause, and this is what is a constraint specification, right, on the template. So the constraint specification basically expresses the things that are in the requires clause. Constraint satisfaction looks at all those specified constraints and makes sure that they're actually satisfied. One way to satisfy them is to look up the models for those that correspond to those specified constraints. Now, the notion of a model here is, don't confuse that with concept maps, for example, because a concept has to have a model. You have to have a way to say this type satisfies the requirements of this concept. That is independently from saying, providing a user with a mechanism by which he can state that the type satisfies the concepts. Concept maps allow us to give the programmer power to say, I specifically am saying that this type satisfies these requirements. But concept models still are an essential part of concepts. So the concept map allows me to explicitly express a concept model and have more control over it that way. Constraint satisfaction kind of looks up for models, and if you're using something like implicit concepts, for example, then if it can't find the model, it's going to try and generate it implicitly. But you still have to have models internally. So from an implementation perspective, and this is kind of how it looks in concept Clang, the concept definitions are declaration contexts that hold a number of declarations. Requirements are represented as declarations. Here, refinements are also treated as a special case of requirements. So we do have them here represented as containers of these things called concept model archetypes. Naturally, for constraint satisfaction, it results in a container of concept model declarations. But here, the constraint specification are expressed as concept model archetypes. The distinction between those two simply boils down to the fact that the concept model archetypes act as placeholders for concrete concept models. So where a concrete concept model is satisfied, the concept model archetype is specified, right? You specify your concept model archetype to represent the specified constraints, and then you satisfy a concept model, but they're all kind of using the same internal data structure, but differently. I do have these notions of substitution versus satisfaction. So where you satisfy the requirements for a concrete concept model, in the model archetypes, you actually substitute them. So this is just to show you the kind of level of details that goes on at the infrastructure level in concept Clang. And to kind of summarize what is going, I mean, there's a lot more that is going on, but to summarize, I want to point out that essentially all of the requirements are represented as declarations, and you have refinements here acting on concept declarations as constraint specifications act on template declarations, because the concept definitions themselves are also template declarations. So noting these kind of properties allows us to actually identify the specific ways in which different designs actually differ from one another. And there aren't that many of them. Here, this is a summary of what I have identified. So, each column here represents a particular salient property, as I like to call them. The first two rows show what each design actually states as what to do about these components. This is how it is implemented at the infrastructure layer of ConceptClaim. Now note that this infrastructure was actually designed in the, I didn't look at the pre-Frankfurt proposal or the Palo Alto proposal to figure out how to actually implement the infrastructure. I based most of the design of the infrastructure on literature on concepts general, like the elements of programming book and related things. Then, when I looked at the pre-Frankfurt proposal, you can see that all that I actually have to do on these salient properties is very little. I have to add a new data structure here to represent the specific requirements. And then we do have a little bit of additional things to do here for the Palo Alto instantiation, including actually explicitly disabling explicit modeling. So what I want us to focus on for the rest of this talk is that one component over there, the checking of the bodies of template definitions. So you see that where the pre-Frankfurt design does name lookup in constraints, the Palo Alto design does what I call expression validation, which is the matching expression against the use patterns. So it looks something like this, right? Here I have a function that is constrained by some concept C, and I've defined this concept here. This is using pre-Frankfurt syntax, and that one is using Palo Alto syntax. Now, one point I really want to make here is that a lot of the discussions are really based on syntactic differences, which really have no significance when it comes to implementation, or has very little significance implementation-wise. So here, the way that it works in pre-Frankfurt is that the requires clause introduces a new scope, a new lexical scope for name lookup. So, and when this is parsed, essentially a new declaration context is introduced in this context. Yeah, I use declaration. It's introduced here, and the way that this is parsed is this declaration is actually substituted. Well, there's a type substitution that replaces occurrences of P here with T. So this foo acting on P's here becomes a foo acting on T's here, and it is injected into this scope. So in order to check the body of this function, when when this function call is being checked, a name lookup will find this declaration, and because A is of type T, that function call will succeed. Now, when it comes to the Palo Alto proposal, things get a little bit tricky because it is not specified anywhere how to do expression validation. It's again part of my job to figure out how it is actually going to work and if it is going to work correctly. A lot of the things I've had to do with the Palo Alto design is to actually figure out different ways to assign semantics to assign language mechanics to the proposal and implement them as well. I've identified about 4 variants so far. So now expression validation is not specified, but I do think that when it does get specified, the behavior of it is going to be either similar to what we're currently doing with the pre-Frankfurt design or something else, or maybe something like weak hiding. I guess I'll just wait to see before I know for sure. So for the time being, I'm assuming, because you can kind of, when you look at these two, you can kind of see some sort of isomorphism between the two programs, right? So I'm assuming that requires clause here implicitly injects the declarations like this one in that scope. And I'm going to continue my, analysis based on that assumption. Eventually, what we're going to see is that, especially, well, let's not get to that. So, moving on to the name binding framework. Is there any questions so far, by the way? Please. No? Okay, good. So, I presented this last year, actually. And what this is about is to basically find a simpler way to talk about name binding, or if you will, name lookup or name resolution, however you call it in your specific context. That terminology actually changes from one language to another. So what we essentially want to do is take a reference like that one, like the function called to foo there, and based on the scoping rules of the language, identify several scopes that are contributing to the binding of that name. And eventually what we want to do is figure out which one of the foos that are available in those scopes is actually the one that that function call refers to. So we did that using some scope combinators and a language concept. So you end up with expressions like this one to express how this name is actually bound. In this particular case, that function call actually fails, but we're going to get to that soon. So the scope combinators, which are things like this, allows us to express the scoping rules of the scoping rules as defined by a language. And the language concept allows us to express all the properties of name binding that are not captured by those combinators. And it turns out that we can actually reduce all those properties in terms of only these three main properties. How a reference actually matches the declaration, which is usually by name, but sometimes there is normalization and several other things that come into play. How to select a best variable declaration when you have a set of declarations. Usually you can think of it as overload resolution. And also how to interpret ambiguity. I mean, usually ambiguity is an error, but that doesn't always need to be the case. So we kind of like have a lot of things going on using that. In this particular case, both declarations of foo in NS and in the outer scope are both matches for that reference, but only one of them is variable. So in that case, both declarations will be, matches to the reference, but the only one that would actually be can result from this particular property is the one that is variable. So the scope combinators, there are 4 of them. The first 2 ones are essentially the most common ones, the programming languages 101. The hiding combinator allows us to express shadowing, right? And the merging combinator allows us to talk about, yes?
I have one question about the earlier slide. What if the call fails if there's no ambiguity?
What if the call fails?
Why is it denied?
Oh, here? Yeah. We'll get to that. Hold on to that. Yes, it's coming. Oh, I should repeat the question. I'm sorry. Oh, okay. Merging is usually the alternative to shadowing, right? You see that with when you do module imports or namespaces using declarations. Now, opening was an interesting one. So based on just hiding and merging, we were trying to kind of push the envelope and see, can we identify a lot of different rules out there for name lookup or name binding and see if we can express them only using hiding and merging. And then we came across argument-dependent lookup, and it was not possible. So we ended up having to introduce this one combinator in order to express ADL. Well, it was possible, but only if we complicated our hiding and merging combinators enough, and we didn't want to have to do that. And then we were able to introduce weak hiding as some sort of a sweet middle between hiding and merging. Now, here are the combinators in a nutshell. This is actually the entire framework, by the way. So bind is a composition of lookup and resolve. Lookup essentially just given a reference in the scope, it picks out all the matching declarations and feeds them to resolve, which then tries to reduce them down to one best variable declaration. When you merge 2 scopes, like in this case, it basically means that given a reference ref, I'm going to look up for the matches in the first scope and then do the same in the second scope and then merge the results. For hiding, I'm going to look up, and if I find something in the first scope, then I'm done and I will return the results that I found. If I don't find anything, then I will go and look in the second scope and return the results of that one. Opening, kind of like hiding, but in the reverse order. So if I find something in the first scope, then I have to go look in the second scope. So in some sense, finding something in the first scope enables me looking something up in the second scope. Notice that all these 3 combinators, resolve doesn't show up anyway. It doesn't, yes?
Shouldn't in an open case be the first branch of the condition be the union of lookup in S1 and S2? Because in ADL, if if I then go to look in associated namespaces, those are added to the results from the directory.
What was the first sentence of your question? I'm sorry.
So in the third line, where open is defined as if I find something in S1, then I take the things I find in S2. But shouldn't I take the things that I find in both S1 and S2?
It depends on how you use it, right? But in the particular way in which we used it, this is actually the way that we want to define it. Because presumably, you still want to be in control of what you do with what you found. So like, if you actually really want to do what you did, then you can always union S1 with, yeah.
Take this and union it with the
Yeah.
S1.
Okay. So resolve doesn't participate in, oh, I'm so terrible about it. I'll get better, I'm sorry. Resolve doesn't participate in the decision of which scope to process. With weak hiding, it actually starts participating. Now, the idea here is that when you're using something like hiding, you can actually have unviable declarations hiding viable declarations. But when you use weak hiding, only viable declarations get to hide other declarations. Okay? Okay. So these two are special cases of a ternary combinator, and there's a whole range of other work that we can do on that. Based on that. Weak hiding is for Sibel's concepts, and this is for ADL. So now let's see. Answering your question now. So this is the example that we had earlier, and that's the expression of the scoping rules for this function call. And what it essentially says is, I have this test scope here, and I have this other scope NS, which is the merge is requested by the using declaration here. So because of the using declaration, this is going to be looked up according to test union NS, and the whole thing hiding the surrounding scope. Right? So now what happens here is that name lookup is going to find this foo, and it's going to stop there because it doesn't check to see if the declaration is even viable. And when it stops here and returns this one to resolve, resolve is going to say, wait a minute, that declaration is not viable, so the call fails to bind. Okay? Now,
And that's what our compilers do now.
yes.
Apply those.
Mm-hmm.
Is there a reason why they do not consider the same namespace that test is declared in?
I don't know. I'm just interpreting the specification. That's the quick answer I can give you. Yeah, I mean, I guess expressing things like this allows you to both see what it is that we're currently doing and try to make sense of them, and maybe improve them also in some way. I mean, my way of improving is to introduce weak hiding, but we'll see. So, with argument-dependent lookup, this is a variation of the previous example, right? And it is a little bit different in that now we have an input argument here to the function. Now, ADL wants that whenever the argument is such that its type was defined in a different namespace, like here, then that namespace should also be taken into consideration. So you'll have something like this, coming back to your question earlier. So in this case, we have test union with NS, and then we have NS enabling ADL when test disables ADL. So finding something in NS actually allows you to look up in ADL, but finding something in test disables you from looking up in ADL. So this function call actually succeeds because ADL is enabled. We found something in NS, so we can actually go in ADL and find the viable declaration. Now, if I add the declaration here, then the call fails to bind because ADL is disabled. So we can now, and this scope expression is only for this particular example, and we can generalize ADL based on similar observations and get something like this as the final formulation of argument-dependent lookup. And it kind of highlights also how ADL is enabled in different ways based on different contexts. You can also kind of like play around with this depending on where the name binding is triggered from. Yeah. So again, for more details, look at my talk from last year because it definitely went over. I mean, I also looked at uses of operators in that one. So there are several applications for this that I cannot get into here, unfortunately. Applications beyond C++, there are things like type-directed name resolution, which has been proposed in Haskell as a way to exploit the power of the dot notation, so to speak. We can kind of like use our framework to clarify some of the discussions that are going on that end. We can also kind of like take a closer look at type signatures in Haskell and say, wait, is there actually a way that we can have these type signatures be something more than pure documentation? Maybe it can actually start acting more as a specification than as a documentation, depending on how we define name binding. You know, the short story is that if we include type inference in our definition of name binding in Haskell, then we can actually have type signatures behave more as specifications than documentations. Other applications are in compiler integration. So we have been looking at integrating these scope combinators in real compilers, so to speak. Well, we've started with language C and featherweight Java, and our intention is to eventually go into more mainstream compilers. And we can also use it to introduce weak hiding. In fact, so the thing was, we had this idea of weak hiding first, but we were really having a hard time talking about what it is that we were trying to solve and what the solution was. And that's kind of how the name binding was born, right? It was born so that we can actually talk about this. So with weak hiding, we take our example from earlier again, and this code still fails to bind. But now, notice that test here is hiding the outer scope. If the relationship between test and the outer scope was such that it was weak hiding instead of hiding, then we will be able to capture the fact that this is actually not viable for this call, and then give the outer scope a chance to for resolution. So we will come here, and this will not be viable, so we will go on the outer scope and we'll find a viable declaration that the call will actually bind successfully. Several things we can do with weak hiding. In the general scope of things, we can do implicit disambiguation. Usually we're used to doing syntax disambiguation based on types or based on the module system and things of the sort. But with weak hiding, we can actually do implicit disambiguation based on the constraints if you're using generic programming. We can use it to also satisfy that we're transitioning from C++ without concepts to C++ with concepts in a safe way or sound way. We want to make sure that programs that are actually invalid that we have not been able to capture so far can actually be captured. We want to make sure that programs that are supposed to be valid can continue to be considered valid. And we want to do all of that with as minimal changes in existing implementation as possible. So we actually want to do this without changing the bodies of templates. I should be able to take any template declaration that we currently have, and all I have to do is add the constraints and not even look at the body at all. And I want that to work. Yes?
It seems weak hiding is more intuitive from a programmer's perspective, that would give opportunity for the function that is actually viable, but to be successfully found by the compiler. Is this something you're trying to move towards to weak hiding? Because I think the way I understood it earlier, it's not implemented right now.
Okay, so the question is weak hiding something that I would like to move forward to because he thinks that it's not implemented right now? It is implemented right now in concept Clang. It is something that we would like to move forward to because we believe that any of the alternatives that we currently have will break existing code. It may not break it on the obvious pieces of code that everyone uses every day, but at least in the long term or in the general sense of it, it will break existing code. And the only way to ensure that it doesn't, that it behaves properly, so to speak, is to use weak hiding. So we can also use weak hiding to experiment with various properties of name binding, like changing the meaning of ambiguity. And last year I talked about parameterized weak hiding, for example, which allowed us to kind of say that, well, so long as I am in a constrained environment, ambiguity is not going to be an error, but once I'm outside of a constrained environment, ambiguity is going to be an error as usual. Those kind of things. And all these kind of like exploration led us to this implementation for weak hiding. So if you were wondering if this thing is actually implementable, it is, and it's actually very, well, I don't know about easy, but all you have to do is take your current mechanism for name binding in your compiler and just make it iterative in a way that behaves differently based on in different contexts. So I actually have some sort of a mechanism set up for that too, how to identify all the different name binding mechanisms in your compiler and just, how can I say, automatically two-stage all your declaration, all your Oh yeah, all your functions that are supposed to be doing, that's supposed to be binding names. So the biggest question is, if I have a template like that one, and right now it is considered valid, once I add concepts, is it still going to be considered valid? If not, is that what we want? So it turns out that because the requires clause introduces a new lexical scope, which injects a function foo in that scope, a function call like this one, which was successful, which has been successful type checked so far, will be rejected now. Like that. And like I said, expression violation is still not specified, so we're assuming that there is an implicit declaration that is injected there. Yes?
So putting the required clause puts constraints on T, and therefore constraints on A, and it doesn't put any constraints on foo 1.
Well,
So that would be the,
so long as name lookup is concerned, it doesn't know that.
yeah, but like conceptually, you would like to think, well, look, I'm only trying to constrain T here. Don't mess with my foo 1 function.
And that's, yeah, so that's kind of what we're trying to achieve with weak hiding, right? Because you're trying to say, well, for this particular case here, please don't stop, keep going.
So it's just trying to constrain one thing.
Yeah.
Can you achieve the same thing by unioning the name?
That you can we achieve the same thing by unioning the scopes? So yeah, that's what I'm saying. The two alternatives we currently have, whether you're doing Palo Alto or pre-Frankfurt, is to either have these things hide the outer scopes or have them union with the outer scopes. But you kind of like, it's a little bit dangerous for me to rely on unioning, and there is actually a condition that I have to find to express this, to kind of talk about the case of unioning, which is going to come a few slides later. Okay. Yes?
So this weak hiding, one of the motivations for it is that you won't have to rework the body of your functions when you insert concept declarations to them. And in practice, though, is it going to be reasonably likely that code will not compile? Like the current code that's out there in the world, if you add concepts to them without weak hiding?
You can actually find existing code that will break without weak hiding. I do have some practical examples coming up on that. Oh, the question was if this will actually break existing code, practical existing code. And my answer was yes. Okay. So yeah, the condition I was talking about for unioning is this, right? The constraint check forwarding condition. And to kind of very well motivate this, I want to look at another pseudo-generic example. So here I have my function constrained by some concept C, which again brings in the foo acting on T. But also I have these convertibility options. So I'm saying that things of type T2 should be convertible to T1. B should also be convertible to T1. So if you just look at these constraints here, you see that all these foos should refer to the same foo, right? Are you convinced that all these foos should refer to the same foo?
Never convinced about anything about ADL.
No, this is not ADL. But this is constraint. This is a, constraint templates.
You would look up, no one's sure about concepts.
Yeah. So, so we have cases like this, and actually in the pre-Frankfurt proposal, these will actually both be bound to the foo in the concept, as I think one would expect, as expected. But then using the Palo Alto proposal, it's kind of tricky because even though the Palo Alto proposal defines the convertible concept, it doesn't allow the compiler to explicitly capture that convertibility. So at this point here, the compiler doesn't know that, I can actually, that foo in the concept is actually viable for this call, because there is no explicit conversion operator that is injected by this convertible concept. So in this particular case, you actually have two things that may happen. Either these function calls are going to be rejected because this is supposed to hide the outer scope, or if you use merging, you're basically having this behave like that. And the question here is, if we do decide that it's okay to basically have this become that, then is that the case that we always want in general? So is it the case that using the outer foo is always leads to either the same behavior or a preferable behavior than using the foo in the concept? What did I mean when I wrote this? And is what I mean actually being what is observed? Is that what the compiler actually understands? So I figured that I don't have an answer for that, but in order for merge to be okay here, this condition has to be proven to me. And that's what I call the CCF condition. Okay? So using merge makes things subject to CCF because you can have calls like this bind to outer calls even though you have declarations in the concepts. So practical examples. Now there are several ones that I've gone over. There's STL rotate that I use to kind of like show the perspective of, I guess, the regular C++ practitioner. And then there is this cool thing called Planoptic photography where you do image rendering that I actually use as an example of the perspective of a novice to C++ that still wants to use it to do, things that are actually popular right now. Here, I don't know if I'm actually explaining this in this talk, but something being subject to CCF doesn't necessarily mean that weak hiding is not needed. And some of those examples actually show that require extensible structure. So I guess right now I'm trying to kind of like go from this and dive into the extensible structures parts of my talk. So I'm going to focus on these two ones for now. And actually, I showed some of these examples last year too, and we can talk about this off topic, I think. I mean, I'm more than willing to go over them in greater detail. So something that I noticed in the STL rotate example, for example, is now you have these binary operators that are all introduced by the random access iterator. Now, for this particular plus, it's okay because the way that the random access iterator is defined in the Palo Alto design is that the result of last minus first should be of type difference type of I, which is what is expected for uses of plus. So that is okay. But then this one is not okay. And it's kind of interesting because even the Palo Alto design, it specifically states that difference type of I here is actually assigned integral. But it states it the same way that it states convertibility. It still doesn't inject syntactic conversions from integers to difference type of I. So as far as the compiler is concerned at this point, the plus in random access iterator is not viable for this call, and that call actually gets rejected. Yes?
Is there some notion of constructor for this different I, so the constructor
The question is there a notion of implicit constructor from integer to difference of type I? In this case, no, because we're also treating, once you're in a constraint template, all of the generic types, all the types that are dependent on the template parameters are treated as non-dependent. So at this point, you have to actually you want explicit conversion at that point. So for Planoptic rendering, this was actually, this has been improved from a class project that I was doing on simulating the capture of Planoptic images and rendering them and all those things. So the important thing here is that we have three kinds of move. Now, when you work with images, it's very important to avoid copying whenever possible. So I want to be very sure that my things are being moved when I need them to be moved and how I want them to be moved. So I have my own moves here, one acting on something of type radiance, the other one acting on something of type radiance type, which is an alias for the boost multi-array, and another one here acting on pixels. Now, this, when in moving to constraints templates, this constraint injects a move acting on pixel types, which covers this particular move. The other ones are not covered, but that is okay because they were not intended to be covered by the constraints. So I have to provide my own move for those in some way. For these two moves, I can actually reuse student move, which is very important here because every time that you can use student move, I would say use it because a lot of work went into designing student move and making sure that the move semantics were actually compatible with all the features of the language like exceptions or overriding and all that stuff. So I would always prefer not to have to implement my own move if I can, unless I cannot help it at all. So these two, I can actually use student move because here I have access to radiance. And that means that I can extend radiance with my own move constructor because that's how student move works. To use it, you need to extend your data type with the move constructor, right? So I can do that here for radiance. I can probably also tell that the user of my function is going to do that for pixel type. The user of, yeah. And, but for this one, I cannot because that is of type multi-array. And I don't have access to multi-array, which is in the Boost library somewhere. And even if I have access to it, I probably don't want to be messing around with it. So, yes?
Why do you move a allocated resource? I mean, it's returning a pointer to radiance, right?
A pointer to, oh yeah. Yeah, that's a flaw. Good catch. I shouldn't have knew there. Okay, sorry. Yeah, well, so if you want to rely on compiler optimizations, that's something that we don't want to do here. Because also the point of this example is to kind of highlight the kind of issues that people might actually run into, whether they're, even beyond relying on compiler optimizations. So, so for this one, I don't have access to multi-array, and I have to implement my own. But like I said, I still want to be able to exploit all the work that was done on student move. So I want to basically just do something like this and implement that in terms of student move. But student move, if student move doesn't find a move constructor, it will default back to a copy constructor, which is the last thing that I want to happen. So I decide that I can actually provide my own move constructor for that particular type. So in here, I can express a syntactic requirement for move constructing things of type T. And then here, I can constrain this by that move constructor. And doing this will have student move find the right move constructor for my type. Now, at the point of use, if I'm using something like radiance type, then how am I going to provide my own implementation of this thing to radiance type? Well, in this case, there is no way that I can do that using an implicit modeling mechanism. I have to use concept maps. Sorry. So I have to use concept maps. RT here is short for radiance type. And by doing so, I can provide my own move constructor here without having to go back to the internal implementation of Boost and extending radiance type and all that stuff that I would have to do. So when I use move on rendered, what the instantiation is going to do is, well, when I move on rendered, constraint satisfaction is going to pick up this concept model that I just defined, and then it's going to transfer the appropriate move constructors to the instantiation of student move. And my program would work just fine. Okay? So that brings us to structure opening archetypes. The essential idea is that if I have a data type like that one with foo, with the function foo in it, and I want to extend it with something like bar, then I can do that using concepts and associated member declarations. So I can use the concept to encapsulate extensions to existing data types. And then I can use concept maps to provide implementations for those extensions. And I can define my generic algorithm this way, and la partie est jouée. So the SO archetypes actually are not visible to the user. These are internal implementation artifacts to concept Clang. And there is a whole other mechanism going on here. I mean, there's a distinction between two different kinds of archetypes, elementary and joint archetypes there. This one acts on restricted scopes because we do have a sense of several different copies of archetypes for T for different concepts that we need to merge somehow so that within the body of a concept, you can only see one T. So that's what we need up there. As far as the compiler is concerned, every time it encounters an archetype of something, it treats it as that same thing as well. So an archetype of X is an X, up until lookup is requested. And then when lookup is requested, there are several paths that lookup may follow depending on the kind of the archetype and also the purpose of the lookup. So if you're doing lookup based on for weak hiding, then it's going to follow a different path. And if you're doing lookup for purpose of, okay, I'm looking up in this join archetype, then it's going to look up inside all the archetypes that are merged into the join archetype. And if I'm looking it up in an elementary archetype, then it's going to follow the refinement path. And basically, all these archetypes also kind of follow the same implementation structure of simple function calls. So at instantiation time, they are rebound the same way that function calls are rebound at instantiation time. Oh yeah, I think I've lost you guys. So why did I care about this? It was kind of like it was related to the expression problem. This is not a new problem. Again, it's been around forever, and it has been solved both in functional and object-oriented languages. The solution is used every day in functional language type classes, but then when it comes to object-oriented languages, for some reason, I don't know why it is, but I did not see any mainstream OO language actually eager to adopt it. And the only times I see extensible structures in a language, it's always in the form of this new language or this extension of this other language. Like multi-Java extends Java in Ruby is a completely new language. And there is a vast array of work going on just defining these extensible structures. So I don't know what the right answer is, but it kind of like triggered me a little bit to observe that. And I was thinking, perhaps if I bring something like, you know what, if you actually just have concepts, then you get all of that for free. So whatever the reason is that you are not, that you're reticent to adopt this feature, you can just not worry about it anymore if you have concepts. So, how am I doing? So based on these things, here is a kind of like a summary of what I've been able to come up with so far. So these are different design variants that I have identified for the pre-Frankfurt and the Palo Alto design. I did not think that I would have time to get into the details of all these design variants here, but I just wanted to highlight that they all kind of preclude or allow the exploitation of some of these sub-features in different ways. So the dark bullet points means that it not only supports these particular features, but also it allows you to exploit it to the full extent that we can, that we know to exploit it so far. The lighter ones mean that it's completely precluded. And then these ones with the circle in the middle means that, okay, it is supported because it's basically an essential part of the infrastructure, but it cannot be exploited to the extent that will be great to exploit. So things like name rebinding and syntax remapping have been discussed in previous work. Name rebinding actually allows you to ensure one particular an important property of the safety that concepts bring us is that if constraint satisfaction succeeds, instantiation should not fail. So successful constraint satisfaction implies successful instantiation of the function. And it's very important that that condition is not broken. Well, it turns out that if I have something like concepts light, then I don't have name rebinding, so I don't have that guarantee that constraint satisfaction failing will not, I don't have that guarantee that constraint satisfaction failing will ensure that instantiation succeeds. And there is actually this program that I submitted a few years back to the committee. And actually last year when Andrew was talking here, I did ask him about this question. And it was basically referring to this example. And he did tell me that concept light cannot do that. Now that is something that I hope that the next iterations of concept light would actually address. Because basically the idea here is, there you have that function again. That one is using implicit convertibility. And you say that T1 is convertible to T2, which means that foo in that context should be binding to the same foo that is bound to A and B. Do you guys see that? Can you see that? And then somehow, when I come here at the point of use, constraint satisfaction succeeds because all that constraint satisfaction is concerned with is whether this function is actually valid, and also if B is convertible to A, which is the case. But instantiation fails because in order to instantiate foo of A there, we have two equally viable declarations. We really need things like that to be captured by the concept system. And as of now, it's not. So, conclusion, yay. Implementing concepts for C++ actually leads to theoretical advances, not just in C++, not just in concepts, but in the areas of expression problem and name binding in general. So it's more general to program languages. These are a listing of all the contributions so far that we are going to continue working on. I'm looking forward to actually completing concept Clang, right? So right now we have, we've made some progress. Like you can actually go and use it on very, very simple cases. So what I like to call the Halo world of concepts, which is like the apple-to-apple program, I have certainly checked that those things actually work on the different variants that I'm supporting. I would like to investigate the CCF condition further and make sure that there is actually a way to specify a class of problems for which that condition can actually be proven valid, right? We want to integrate the scope combinators in current compilers, and we want to formalize the SO archetypes, relating them more to the research that is currently going on, and further our comparative studies of the design space of concepts. So far, there is at least 30K lines of codes. Like I said, it's open for contributions. I know I've received those emails, and now I'm saying that it's going to be possible now. The essential structure are implemented. The two main things that are missing right now, which I'm going to be working on after this meeting, is the structure opening archetypes, and also one particular variant of Palo Alto design relies on translating use patterns into pseudo-signatures. And that's it for today. Thank you. Now. Okay. Yeah.
Question about the implementation of the open class portion. It seems that would require you to have added new visibility rules in order to be able to see the private internals to implement the move, or other extensions to the class.
So the question is, does implementing the structure opening archetypes, will that require new visibility rules? Yes and no. I mean, so the only trick that I have to do, if I can, I need to go back to that. At this point, right? So here is the call that we're trying to instantiate, right? Constraint satisfaction has already found the map that we want. Now, the only thing I would have to do, as of now, is to make sure that the concept model is transferred to the instantiation of move. So what happens, this is speaking from the structure of Clang, is when this is instantiated, I actually have access to the body of this, and I can just basically add additional information about the instantiation of the body, and say, when you instantiate this thing, remember that I do have these concept models that you should take into account. And then, in the process of instantiating the body for this move, when it comes across this pseudo move, it will do the right thing.
So it's not open in the sense that you could extend the class with arbitrary additional behavior. It's allowing you to have further visibility in order to exercise its functionality in ways that you couldn't from the scope that you were in. Is that a fair way to say it?
I'm not sure if
I
yeah.
think the question is, how do you implement the concept model for that RT,
Yeah.
that move construct.
That's good.
Like in the previous slide. Yeah, how do you implement that? Because that's going to need to get to private internals of whatever RT is, right?
Yeah, and that's fine. You will find it because RT at this point is not an archetype yet. So this one, so this is going to be parsed as an archetype, but the archetype has access to the explicit
How do
RT.
you actually
Yeah.
implement the move that you want on boost multi-array?
How do I actually implement the move that I want to boost multi-array? Then I would do this, and I would put the implementation in here.
Yeah, but how do you?
Oh, I don't know yet.
Right, because the problem is if boost multi-array doesn't have a move,
Mhm.
you want to apply one.
I
you won't
have-
be able to get at the internals.
I have access to the internal data. Forget what, there is way to access
Gives
the
you
internal.
enough.
Yeah, it gives me enough that I can actually manipulate the internal data in the multi-array,
Seems
yes.
to me it would require new visibility rules in order for this to be able to say if it's truly open class where I'm adding functionality. At that point, I need to see the privates to the private members in order to.
Yeah, and the thing is that looking something up in the archetype knows to also look it up in the concrete type itself. So it will find everything I would normally find in RT as well.
But if boost multi-index or whatever didn't have enough functions in its API to give you access to its internal pointer or whatever, then
Yeah, that-
you couldn't implement it.
You couldn't, but in this particular case we can. So why not?
It's just that they give you enough to do it, but they just didn't happen to do it themselves because it's old code that never wrote a move.
I think it's called Elements or something. Anyways, they gave me a way to get access to the internal data. Yeah. Yeah?
You mentioned in a later slide something to do with, certain type things that you can do in these other languages, but not in OO languages. I didn't quite catch what precisely you meant by that.
So the question is, I mentioned something about things that we can do in other languages, but that we cannot do in OO languages, and he wants me to clarify. Right?
One before that.
Oh, no, sorry. This one?
Yes.
No, so my point was the solution in functional languages is to use type classes, and people use that all the time. But the solution in OO languages is to use extensible structures. And I'm not sure if I can say people use that all the time, right? People only use it in the context of new languages. So if I have my C++ or my Java, why am I still relying on things like the visitor pattern or double dispatching or all these other mechanisms that are supposed to be too complex and resolve, and that are supposed to be too complex, and then also that I'm supposed to be able to use extensible structures to avoid using? Yes.
So, like, for example, Objective-C has categories which allow you to extend things of that. I'm wondering, is that not considered a mature object-oriented language, or is that, like Scala has type classes as well.
Yeah, so the question was, other languages like Objective-C of Scala have categories or some ways to do extensible structures, you meant?
Yeah.
Actually, to be honest, I have not looked at those languages. I do know there is a paper that did talk about a way to do, so I think the paper was called Independent Extensible Solutions to the Expression Problem. And that one actually explored certain features in Scala of how to do this. But basically what it boiled down to was, you're going to have to do all these things that essentially look like concepts. And I actually looked at some of the examples in that paper and rewrote them using concepts and actually got rid of some of the complexity that even that solution still had as well. For Objective-C, I'm not very familiar with that one.
Categories are pretty much kind of like being able to do in Ruby, where you can just reopen the class and add stuff.
So I think that the point I was trying to make here was that why is it that instead of just adding it to Java, I have to go and create multi-Java? Why is it that I don't have any C++ yet? Why is it that this guy created Ruby, presumably with the intention of also supporting extensible structures? As Ruby supports a lot of different things, but it also supports extensible structures specifically.
Is the
Open classes, I should say.
the Objective-C stuff new?
No, it's been there forever. I mean, I think Ruby does it because it got it from, because didn't Smalltalk do it originally? And I think Ruby got it because they're trying to do a Smalltalk-like object-oriented system. And I think that's where it came from in Objective-C as well, but as far as I know, it's been in Objective-C forever.
Okay, thank you. I mean, that's information I didn't know, so. Anything else?